Hello everyone, welcome to the course on measurement and instrumentation, and today is the fourth lecture of our 12th week. We are discussing the data acquisition system, and today we are going to discuss about the last segment of any data acquisition system, which is the display devices. Okay. Why I am saying the last stage of any measurement system? Because here you will see the data that you have already acquired, maybe in continuous form or maybe for the instantaneous part. For example, say if you are acquiring say temperature for every 1 second with the data acquisition system, you had other part, and say at the end you have this display device. Okay. Whatever data you have acquired, say for example with the transducer you have acquired a temperature, say the temperature is 30 degrees Celsius at t equal to 0, okay, and it is say 30.5 degrees Celsius at t equal to 1, and say 30.7 degrees Celsius for t equal to 2, and say 30.1 degrees Celsius at t equal to 3, okay. Ideally you can have display devices which can show you all this data in one go. Say for example, it can show you say 30 point something, say 30 degrees Celsius for t equal to 0, then it can change back to 30.5 at t equal to 1. Similarly, it can change back to say 30.7, okay, at t equal to 2, or you can also visualize it in one go. Say for example, you have data something like this, say on this scale, say this is time and this is say a temperature. I am not, usually it is converted into voltage. I am showing you the actual figures, okay, forget about voltage right now, okay. So 30 degrees Celsius, it goes to say 30.5, say at t equal to 1, then it keep on increasing, okay, till t equal to 2, and then it come back to 30.1, say at t equal to 3, okay. So you can see this data continuously on the screen. So you have display devices which can have this kind of capabilities, okay. That's why I mentioned that these display devices are actually the last stage of any measurement system, okay. Now the data presentation stage consists of display devices as well as you have recorders which can record the data. Sometime you may require this data at the later stage, and for that you may have to store it also, okay. So in fact, usually the first stage is the display device where you can visualize the data, and then the second stage is the recorder stage where you actually have a memory where this data can be stored, okay. Now the choice between the display devices and recorders depend upon the expected use of the output and the information content of the output, okay. The output devices can be classified into different types based on the nature and use of the output. You can have a single number output device. You may also have a time domain output device, and sometimes we also require machine interpretable output devices. Let's see quickly what this means, okay, and what particularly the machine interpretable devices which are in much more demand in current generation, will see what it means, okay. Let's see first the single number output devices, which was more popular in 1980s or so, okay. These devices display a single value when the measured quantity is time invariant over a short interval, and examples include indicating instrument and digital displays, okay. Although it is not obsolete right now, because we have seen several indicating instruments that are still existing and we use it on day-to-day basis in the laboratory, okay. However, these kind of display systems were very popular earlier when the concept of displaying the measured data came, okay. Then we have time domain output devices. These are used when the output varies with time and waveform or signal shape is required, okay. Devices like the CRT that we have discussed earlier, recorders and magnetic tapes are used for representation and storage of time varying signal. Now we have even advanced ways of storing these data, right. We have USB cables, you can have USB ports where you can put your pen drives and store the data, or you have SSD hard drives and so on, okay. Now the world has moved much beyond than the magnetic tapes and other things, okay. Then we have machine interpretable output devices. Now the two output devices that we have just seen now provide an output that require interpretation of human beings. You do not require to feed this data to any machine, or you are not dependent on machine for reading this data. You can read them yourself. For example, if some device is showing you the direct data, say the temperature, you can simply read it, right? Similarly, if it is showing you a certain waveform with time, that also can be interpreted by human being. But for example, if you want to feed it or you want to read it continuously, okay, you may require some machines to interpret the data, and in modern application it is necessary that the output data should be in such a form that it can be read by certain machines. Okay, this machine interpretable output can be read from several instruments, like in the older generation magnetic tapes and other kind of tapes like punched paper tapes, punched cards and so on. But in the modern devices you want it to be read by external hard drive or external USB kind of, I mean in USB also you have now several categories, type A, type C and all. So you want it to be read by these recorders, okay, and the output can be in either analog or digital form depending on what application you are trying to implement these. The machine interpretable output can either be analog or it can be digital. A signal recorded on a magnetic tape in analog form may be useful in activating output devices like CRT, a recorder on an indicating instrument. Okay. Now, electrical indicating instrument we have seen earlier in detail, but I will just recall them so that we are on the same page. Electrical indicating instruments are used extensively for the measurement of current, voltage, resistance and power. We have seen all kind of electromechanical instruments, in our module 2. In fact, we have given week 2 to week 6 dedicatedly to the analog meters. Okay, these instruments are broadly actually classified into analog and digital. We have mostly seen the instruments which were analog in nature. However, we have digital instruments also, like we have digital voltmeters also, which can be used to measure voltage, as well as you can modify it for other measurements also. Okay, analog instruments display the measured quantity by pointer deflection. We have seen pointers for all kind of instrument like PMMC, moving iron, electrodynamometer and so on. Okay, all these analog instrument displays the measured quantity by pointer deflection, whereas a digital instrument indicates the value directly in the decimal form. Okay, the digital meters work on the principle of quantization, where the analog quantity to be measured is first subdivided or quantized into a number of small intervals up to many decimal places, which will give you better accuracy. Okay. Now, the objective of the digital instrument is to determine in which portion of the subdivision the measurement actually lies, so that it can be identified as an integral multiple of the smallest units. We call it quantum or quanta. Okay. The measuring procedure thus reduces to one of the counting, of the number of quanta present in the measurand. Okay. The reading accuracy can be further increased by increasing the number of decimal places, or you can say by increasing the number of quantization levels. Okay. There are several advantages posed by these digital instruments, like the digital instruments indicate the readings directly in the decimal numbers, and therefore errors on account of human factors like error due to parallax and approximation are eliminated. The readings may be carried to any number of significant figures by merely positioning the decimal point. Okay. Since the output of the digital instruments is in digital form, and therefore the output may be directly fed into any kind of memory devices. We can feed it to tape recorders, printers, floppy disk, hard drives, to SSDs and digital computers for storage and for future communication. The power requirements of digital instruments are not as high as the analog instruments, and if you compare between a digital versus analog instrument, the accuracy of the digital instruments are much better as compared to the analog instrument. The best analog instruments are rated usually within plus minus 0.1% of full scale. Digital instruments can be made of much better accuracies. Okay. The reaction to environment is also much better for digital devices. Analog meters movement are relatively simple and will operate under a wide range of environments, while digital instruments are relatively complex and consist of large number of parts which individually will react to change in the temperature and humidity in the ambient. Okay. the resolution of these devices are much better. This resolution is sometimes also referred to the readability, below which differences can no longer be differentiated on any scale. In analog instruments, the limit is one part in several hundreds, while for digital instruments you can make the resolution of one part of several thousands and even of the order of 10,000s. Okay. Digital instruments draw only negligible power because they are mostly IC based devices, and we have seen that analog meters are coil based devices and they require higher input current or voltages. Digital instruments has input impedance of the order of 10 mega ohm or even higher, so it will not load your circuit, whereas the analog instrument may load the circuit under measurement and thus indicate an erroneous result. We have seen this with several examples of voltmeter and ammeters in our discussion in module 2, where we have seen that all the instruments like moving iron, electrodynamometers can be converted to ammeter or voltmeter, but they can load the circuit in which they are being connected. Okay. If you talk about the cost and portability of these devices, analog instruments are extremely portable and usually do not require an outside source of supply for measurement, and these instruments are low in cost and can be moved from one location to another without any difficulty. Okay, because only for devices where we have seen that the control is not spring control, but the control is based on the gravity, there the movement was a little difficult, right? Otherwise it was not that difficult to move. However, if you see for the digital devices, although they require very less power, but then also you need external source of power wherever you want to do any kind of measurement. Although with the advancement in the IC technology and fabrication technology, the portability of these devices has increased a lot. Okay. If you talk about the range and polarity of these devices, most digital instruments are essentially DC instruments which measure up to 100 volt and up to 1000 volt using a range attenuator. For AC measurement, digital instruments use an AC to DC converters, right? Many digital instruments incorporate automatic polarity selection and auto ranging facilities. Now, these features reduce operator training, minimize measurement errors and prevent possible damage due to overload of the circuit. Okay. Now, the biggest advantage that we have seen for digital instruments are freedom from the observational errors. Okay. The digital instruments are free from observational errors like parallax and approximation errors, which was one of the biggest challenge in case of the analog meters. Okay. Analog instruments usually have a scale which is cramped at the lower end and therefore give considerable observational error, particularly for the devices where we have seen that the deflection is directly proportional to I square in place of I. We have seen that the lower divisions are cramped and in the higher regions you have divisions at larger spacing. Okay. So, for these devices even the challenge is even higher. Okay. Also, when using analog instruments, inexperienced personnel often tend to select a scale that does not correspond to the setting of the range switch, thereby introducing large operating errors, which is totally avoided in case of digital instruments, and therefore the digital devices are much preferred for display devices and all these devices are based on electronics rather than electrical devices. Okay. Electronic counter is one such way to implement the digital displays. We have seen that the digital display are nothing but it can be made by a counter which can count the number of quantas. Okay. Now, these counters can be made electronically and we call it electronic counters. Okay. Electronic counters are capable of making many measurements involving frequency, time, phase angle, radiation event and totalizing the electrical events. Okay. The electronic counter normally employs a frequency divider circuit. We call it a scaler. Okay. A scaler produces a single pulse for every set of number of input pulses. For example, a 2:1 scaler produces one output pulse for 2 input pulses. A scaler is essentially a frequency divisor and the basis of counter is basically a frequency division. This is done, for example, by using a 2:1 scaler. We call it a bistable multivibrator or we call it the flip-flop circuit. So you can say that the electronic counters are made up using flip-flop circuits. So flip-flop is essential for any counters, and we have to understand them in little brief. Okay, there are different kind of flip-flops. We have RS, or sometime also called SR, reset set flip-flops, okay, JK flip-flops, D flip-flops, T flip-flops, and sometime we also combine, we have RST flip-flops and all. Okay. A flip-flop, as the name suggests, is a bistable multi-vibrators with two stable state, either low or high. We call it 0 and 1. Okay. The output remain in one state until a trigger is applied which changes it to other state. So basically it also acts as a memory device. Therefore, if trigger is applied when output is in one state, it changes back to 0 state, and if the output is in 0 state, if you apply the trigger, it will change to 1 state, or you can also understand with high and low states. Okay. An RS flip-flop consists of two cross-coupled transistors. This you can see Q1 and Q2 are cross-coupled. This cross-coupling is providing a positive feedback to it, and this is giving it two stable states. We have earlier seen that how a positive feedback can be used to generate oscillations, right? We have seen it multiple places in this course. Okay. The same concept is used in the flip-flop, where the BJTs, are cross coupled in such a way that they are in positive feedback, and this will give you a two stable state or kind of oscillation. Okay. In this example, if you see, both the transistors are Q1 and Q2 are NPN, and the collector of each transistor is cross coupled to the base of the other transistor. The cross coupling between collector and base results in a positive feedback. If Q1 is conducting, there is a large voltage drop in resistance R1. Okay. Therefore, Q1 reaches the saturation region, and voltage VCE at Y is only about 0.1 volt. This is the Y point I am talking about, and this is the Y bar. Okay. So voltage VCE at Y is only about 0.1 volt when this Q1 reaches the saturation. Now this voltage is applied to the base of the transistor, and it is not sufficient to turn on the transistor Q2. Okay. This require a voltage of about at least 0.7 volt to turn it on, considering that this Q1 and Q2 both are silicon transistors. Okay. In this case, the transistor Q2 will be in the cutoff, and under this condition, output this Y bar will be 0 and this Y will be equal to 1. Okay. Similarly, if by some means we can get transistor Q2 to conduct, there will be a large voltage drop across resistor R2, and therefore the transistor Q2 will get saturated, and the potential at Y become 0.1 volt, forcing the transistor Q1 to cut off, and under this condition the opposite will happen. Y bar will be equal to 1 and Y will be equal to 0. Hence, there are two stable state for the flip-flop, and these are Y equal to 1 and Y bar equal to 0. This is achieved when Q1 is on and Q2 is off, while Y equal to 0 and Y bar equal to 1 if Q1 is off and Q2 is on. Okay. In order to control the flip-flop, trigger inputs are applied, as we have seen. If a positive going pulse is applied to the set input terminal, then Q1 conducts heavily, or you can say gets saturated, and Q2 reaches the cutoff region. Similarly, when a positive going pulse is applied to the reset input terminal, Q2 gets saturated and Q1 is in cutoff. Now we can say that the flip-flop is controlled by two inputs, set and reset. When I say set, it makes Q1 on and the output is 1. Y, I'm considering Y as an output. When you are resetting it, it means that you are making Q2 on, and in that case output will be, or Y will be equal to 0. Now the condition S equal to 1 and R equal to 1 is forbidden because it leads to an invalid state. This is, I am telling that this is invalid or this is forbidden because when you say S equal to 1 and R equal to 1, it means that we are trying to get Y equal to 1 and Y equal to 0 simultaneously, which makes no sense, right? either you can have y1 at one time or y equal to 0 in one time. You cannot have 1 and 0 at the same time, right? Therefore, this conditions is forbidden. So, usually this flip-flops comes with a truth table, and this is a logic symbol of a RS flip-flop, for example. Okay. So, this is 2 inputs and 2 outputs, and when you have 0 0, it will show you the last value. Okay, or when you have 0 1, you have 1 1, or 0, you will have 0 1 1. We have seen it is not allowed. Okay, the internal circuit in terms of gate looks like something like this. For RS flip flop, you will see there are other variations of RS flip flop also, but the idea remains same. Okay, the concept of set and reset remain same. Okay, similarly, you can see a T flip flop here. Okay, we call it a toggle flip flop. A train of narrow pulses is applied to the T terminal here. Okay. Now, this circuit uses 2 AND gates, you can see, and a RS flip flop. Okay. Every time a pulse is applied, the output of the flip flop changes the state, and that is why we call it toggle flip flop. Okay. When a pulse is applied, the flip flop is either set or reset depending on the previous state. The AND gate control whether the pulse goes to set or it goes to reset input. Each incoming pulse causes the flip flop to toggle its state from 0 to 1 or 1 to 0. Now, 2 input pulses produces one complete output cycle. Hence, the output frequency is half of the input frequency, and you can say that it acts as a frequency divider. Now, the T flip-flop can operate with positive or negative edge triggering. In some designs, the state changes only at the negative edge of the pulse, while in some it changes at the positive triggering. Okay, but you can see that this is a combination of SR and T. We call it a RST flip-flop. Okay. Now, RST flip-flop combines a SR flip-flop, RS flip-flop, and a T flip-flop. So, you can have capability of set, reset as well as toggle. Please note that for toggling, you will still require another RS flip-flop. Okay, but I am considering that this is inherent into this kind of device. So, you can say that in summary that when you have positive going pulse applied to S, it sets, and finally you will have y equal to 1 and y bar equal to 0, while positive going pulse applied to R will reset it, and at that case you will have output as y equal to 0 and y bar equal to 1, while a negative going pulse applied to the toggle input will toggle this flip flop, and it switches from 1 to 0, or if it is already in 0, it switches from 0 to 1. Okay. Now, based on these flip flops, we can have counters, because ultimately we were discussing electronic counter. I will give you an example of a counter. You just have a look on this configuration. We call it a decade counter, and it uses the RST flip-flop that we have just seen. Okay. Now, 4 flip-flops can be cascaded to act as a counter for the input pulses. Now, a decade counter use 4 different flip-flops. You can see here, okay, and you have A, B, C, D at its input. It also uses, of course, gate, AND gate. Okay. Now, a square wave, we call it clock, is applied as an input, and each flip-flop changes state based on the clock pulses. We have seen that how triggering actually works. Okay. The output from flip-flop A drives the flip-flop B. Okay, I am calling this A, B, C and D flip-flops. Okay, the output from flip-flop A drives the flip-flop B. Similarly, the output of flip-flop B drives the next flip-flop C, while the D is driven by the flip-flop C. Means that you can say that the previous flip-flop is actually driving the next flip-flop. Okay, at the start, all flip-flops are reset so that the input DCBA is equal to 0. On each clock pulse, the flip-flop changes their state sequentially, producing a counting sequence. Okay. An AND gate controls the operation by enabling or disabling pulses to the next flip-flop, and on the first clock pulse, flip-flop A toggles, giving the output A as 1. So, all this DCB remains 0. So, after 0 0 0 0, you have a 0 0 0 1. Okay. With each clock pulse, the state changes sequentially, and then you have all this counting starting from 0 0 0 to 0 0 0 1, depending on, say, when flip flop B gets toggled, you have 0 0 1 0. Similarly, after that you have 0 0 1 1 followed by a 0 1 0 0 and then 0 1 0 1 and so on. Okay. At the 10th pulse, the counter returns to DCBA as 0 0 0 0. This completes one full cycle of the counting. Okay. The counter produces one output cycle for every 10 input pulses, which acts like a frequency of it. Okay. Hence, it is called a decade counter or decade dividing assembly, DDA. Okay. Now, this is a brief about counters that are used in the digital displays. Okay. Now, let us see what are the other ways to have a digital display. So, let us see the digital display methods or methodologies. Okay. In digital instruments, the output devices indicate the value of the measured quantity in decimal digits, and this is done by using the digital display devices. Okay. A digital display device may receive digital information in any form, but it converts that information to decimal form. The input can be analog as well as digital. It may have a converter inbuilt, but it will always process that in a decimal form. Thus, the display device indicates the value directly in the decimal digits. Okay. The basic element in a digital display device is the display for a single digit, because a multiple digit displays is nothing but you can say that a group of single bit displays. Okay. There are various ways of classifying digital display units, like based on the format it uses. For example, it can be classified as planar and non-planar digital display units. Okay. The planar digital display unit will have entire readout character in the same plane, and there are different examples of planar displays. There are like segmental displays, dot matrix displays, projection displays, and some of the gaseous discharge displays can also act as a planar display unit. Okay. The characters are displayed in the different units in case of the non-planar devices. The non-planar display includes some Nix's tubes and display using illuminated lucite sheets. Okay. The segment displays or the segmental displays are very popular single unit display. Okay. And it may be a 7 segment which will only have numeric, or we can also have a 14 segment which can be alphanumeric depending on the requirement. It consists of 7 segment, starting from A to G. As you can see, you have these segments A, B, C, D, E, F and G, and display digits from 0 to 9 by illuminating the proper segment. I mean, depending on, say, in this case, for example, G is not illuminated, so it will show 0. Okay. When all these segments are not glowing, only B and C, then you have 1. Similarly, depending on what segment is glowing, you can have all these numbers. While for the 14 segment or the alphanumeric display, we will have 7 segment A to G and a display digit 0 to 9 by illuminating the proper segment, something like this. Okay. So, depending on your requirement, you may have your own choice of display unit. Okay. Similarly, we have dot matrices. There are different variety of dot matrices available. Okay. Dot matrix display are used for numeric and alphanumeric characteristic. 3 cross 5 dot matrix arrangement shown here is commonly used to display numeric data. Okay. Another system uses 27 dots is shown over here. Okay. This system display the numeric characters as shown in the diagram. Okay, you can see that depending on which dots are glowing, you can have all these numbers. Okay. The dots may be square or round with 0.4 mm side or diameter. LEDs and LCDs are used for display of these dots. For display of alphanumeric characters, a 5 cross 7 dot matrix is used. You can see this 5 cross 7 dot matrix, and using this alphabet A is shown over here. Similarly, you can generate all numbers and alphabets. Okay. In the modern days, this LEDs has been very popular to construct all these displays. Okay. They are used not only in the modern instrumentation, but we have seen that in our day-to-day life for illumination also this LEDs has played very crucial role. Okay. Now, these LEDs are a PN junction device that emits light when current flows through it in the forward direction. You can see one of the cross-sectional view of a LED. Okay. Light is produced due to recombination of electrons and holes at the p-n junction. During recombination, charge carriers releases energy in the form of heat and light, and if the semiconductor material is translucent, the emitted light becomes visible, making the junction act as a light source. In a typical LED, recombination takes place in the P region, which forms the surface of the device. It depends on what fabrication technology you are using. Okay. A transistor can be used as an on-off switch to control the LED. When base current is applied, the transistor goes into saturation, conduct heavily, and in that case the LED starts glowing. When there is no base current, the transistor will be in the off state and the LED will not emit any light. A resistor RC in this case is used to limit the LED current and protect it from any kind of damage, maybe because of heavy current flow or something like that. Okay. There are several advantages of LEDs, like LEDs are small in size and can be used to form high density numeric and alphanumeric displays. The light intensity depends on the current, so brightness can be easily controlled. LEDs have high efficiency and require low power. Okay. They have very fast switching speed of the order of less than a nanosecond, suitable for dynamic displays. They are economical and reliable due to the batch fabrication of IC fabrication technologies, and they are rugged also and can operate over a wide temperature range. Even it can go to as high as 70 degrees Celsius. There is subject known as optoelectronics. If you are more interested about LEDs, you can have a look on any good optoelectronic book. Along with the, this basic LEDs, you will see that there are a variety of LEDs available in the modern scenario. Particularly with the rise of compound semiconductors, the variety of LEDs that are available has grown significantly. Okay. This LED, however, has several disadvantages, like they have higher power requirement compared to the LCDs that we will see in a while. Okay. They are not suitable for large area display because of the high cost that can incur if you talk about large areas, and in those cases LCDs are still preferable. For larger displays, gas filled plasma devices are preferred, but nowadays it is also being replaced by LEDs, particularly with the cost going down for this LED, particularly with the advancement of the device fabrication technologies. Okay. Now, another alternating technology is the liquid crystal diodes or LCDs. LCDs are used in similar application as LEDs, particularly for displaying numeric and alphanumeric characteristic in segment and dot matrix displays. They are of two types. We have dynamic scattering type LCDs and we have field effect type LCDs. Okay. The liquid crystal is an organic compound that shows optical properties of a crystal while remaining in the liquid form. The liquid crystal is placed between glass sheets, as you can see over here, with transparent electrodes on the inner surfaces. Where a potential is applied across the cell, charge carriers flow through the liquid, disrupt the molecular alignment and produces a turbulence. Okay. When the liquid is not activated, it is transparent. When the liquid is activated, the molecular turbulence causes light to be scattered in all the direction, and due to this scattering, the cell appears to be bright, and the phenomena is called the dynamic scattering. Okay. The construction of field effect liquid crystal display is similar to that we have just seen in case of dynamic scattering type of LCD, with the exception that the two thin polarizing optical filters are placed at the inside of each glass sheet. The liquid crystal material in the field effect cell is also of different type from that we have employed in the dynamic scattering cell. The material uses twisted pneumatic type and actually twists the light passing through the cell when the latter is not energized. Okay. Now, this allows the light to pass through the optical filters and cell appears brighter. When the cell is energized, no twisting of light takes place and the cell appears a dull kind of thing, or it will remain in the off state for a user. Okay. Liquid crystal cells are again of two types. We have transmittive type and we have reflective type. In the transmittive type cells, both glass sheets are transparent so that light from the rear source is scattered in the forward direction when the cell is activated, while the reflective type cells have a reflective surface on one side of the glass sheet. The incident light on the front surface of the cell is dynamically scattered by the activated cell. Now, both type of cells appear quite bright when activated even under the ambient light conditions. Okay. The liquid crystals are basically, if you see, the light reflectors rather than being a emitter of that. You can say either reflector or transmitter, and therefore they consume less amount of energy because they are not the light generators. Okay. However, we have seen that LEDs are actually light generators. Okay. The charges are recombining at the junction and it is generating light. Okay. So, the biggest advantage of LCD is in the power consumption only. Okay. So, these LCD devices have low power consumption, much lower than even low power consuming LEDs, and they are also of low cost because you have seen that some organic molecules are involved which can be synthesized in the laboratories. Okay. There are different disadvantages of LCDs, like they are very slow, the turn on and turn off time are quite large, and therefore you have seen that all the displays, even in your mobile devices or in your computers, are now being replaced with LEDs, and only the old generation devices or old generation screens are using the LCD screen. Okay. The turn on time is typically of the order of few milliseconds, while the turn off is 10 millisecond or so. However, we have seen that in LED the response can be very fast, less than even a nanosecond. Okay. When used on DC, their lifespan is quite small, and therefore they are used with AC supplies having a frequency less than 500 hertz. Okay. They occupy a larger area, so you can have less pixels in the same area. Now, if you talk about any digital meters, there are different characteristics, like resolution is one of the important characteristic of any digital display. Okay. So, resolution in any digital meter depend on the number of digital positions used in their display. Okay. So, a 3-digit display can show value from 000 to 999, while smaller resolution of 1 millivolt for 0 to 1 volt range. A fourth digit, usually 0 or 1, is added to extend the range from 999 to 1999, and this addition of this extra 1 is known as overranging, or you can say that I am making this device overranging. Okay. If n is the number of full digits, then the resolution you can say that is equal to 1 by 10 to the power n. So, a 4-digit display has a resolution of say 1 by 10 power 4. Okay. Or you can say that 0.01% or 1 part in 10,000. Okay. Now, similarly, there are other characteristics of digital meter which is of course also governed by the display that it uses. Okay. Like sensitivity is the smallest change in the input which a digital meter is able to detect. Okay. Therefore, it is the lowest voltage ranges full scale value multiplied by the meter's resolution, or you can say that the sensitivity is equal to the lowest full scale value of the meter. Okay. Multiply by the resolution expressed in the decimal. Okay. Similarly, there are other characteristics of digital meters which are directly governed by the display units. Therefore, the display, although it is the last segment, or you can say the last part of any digital meter or any kind of data acquisition system, but it also plays very crucial role in displaying, or it is actually at the forefront of the user. So, it plays a very crucial role in interpreting the data acquired by the system. So, thank you for attending this lecture. In the next class, we will summarize whatever we have discussed in this course over last 59 lectures. Thank you.